Okay, welcome back. In this video, we're going to be talking about slope fields. So slope fields are a visual way to try to envision what the general or particular solutions to a differential equation look like. There are some analytical techniques using integration that help us find solutions that we're going to do in the last video. But here we're just going to be looking at sort of a graphical way. So first let's start off, what is a slope field? What does it mean? So let's say that we start with a differential equation. This one's pretty simple. Y prime equals x squared. So what this means is that I don't know what the general solution is yet. But I know that if I were to draw the function that is the solution to this differential equation, at any given point on that graph, the slope of the graph would be x squared. So whatever the x coordinate is at that point, square it, that would be the slope. That's what this differential equation is saying. The slope, y prime, so remember the derivative is an expression of slope or rate of change. Y prime, so the slope at any point is just the x coordinate squared. So if I have that information, I can actually sketch what's called a slope field. So I'm just going to put a picture of the slope field for this up here. So this is the slope field for y prime equals x squared. So what we've done is add specific points here. So I'll choose a point 1, 1. So right here. Whoops, pen. It's right here. So we've gone to the point 1, 1, and we've asked what is the slope at that point. So we know y prime is equal to x squared, so at that point x is 1, u1 squared. So the slope of the solution function is equal to 1 at this point. So what I've done is I've drawn basically all these are tiny little snippets of tangent lines that would be tangent to the solution function. Because remember, we only know the slope of the solution function at each point. So I'm just drawing little hash marks that have the slope that I calculate. So that little hash mark there has a slope of 1. If I move over to 2, to the point 2, 1, so now I'm right here. So at 2, 1, the slope is going to be 2 squared. So that's going to be 4. So the slope of the solution function at the point 2, 1 is 4. So this little mini tangent line is going to be much steeper than the one at 1, 1. Couple things to notice here. The slope, y prime, only depends on the x coordinate. So the slope of the solution function only depends on the x coordinate. So if you look at any given x value, so I'm going to look at x equals 1, all of the little hash marks have the same slope. So all the little tiny tangent lines all have the same slope. So the slope is constant along vertical lines. My mail just arrived. And on the y-axis where x equals 0, you see the slope is horizontal, so we have a slope of 0. So that's how this slope field is generated. You will need to know how to generate a slope field. A lot of times they'll give you, and we'll do some practice on this, they'll give you certain lattice points and ask you to draw the slope, the little hash marks at each of those points, and we'll look at how to do that. So why do we care about a slope field? What does it help us do? Well, so once I have a slope field, I can imagine, it basically helps outline the contours of the solution function. So like if I think the solution function goes through this point, I'm going to try to draw a curve whose slope matches the tiny tangent lines as I move along. So at this point, as I'm moving to the left, I see that the tiny tangents are getting steeper and steeper. And so I'm going to draw my curve that's getting steeper and steeper. As I move to the right, I see the tiny tangents are getting flatter here, so I'm going to keep my function flat. And then as I start moving more to the right, the tiny tangents get steeper and steeper again. So I'm going to draw my function so that its slope or rate of change matches the hash marks. So if I knew that the solution, so this green line that I drew is a particular solution to this differential equation. There's an infinite number of particular solutions. Let's say I knew that my particular solution went through this point. So if I start here and I start drawing, I'm flat, flat, flat. Then I start getting steeper and steeper and steeper. And in this direction, I'm going to start getting steeper like that. The astute student will observe that the general solution to this is a cubic, which makes sense. The derivative of cubic is squared, but we'll get to that in a little while. So anyway, there's an infinite number of general solutions. All of them essentially have the shape of a cubic. And so that's how you can use a slope field to start to envision what the actual solutions to the differential equation are. Okay, so here's some practice for you all to actually sketch a slope field. This is going to get a little tedious, I'm sorry. So I'll do the first one. I'm going to go ahead and finish drawing these lattice points, and then I'll unpause the video. Okay, so I am going to sketch the slope field for the differential equation y prime equals x. So on each of these lattice points, I'm going to draw a tiny tangent that has a slope that fits this description. So for this equation, y prime equals x, the slope of the tiny tangent is just going to be whatever the x coordinate is. So at 2, the slope of these little tangents is going to be positive 2. Yes, I'm totally just guesstimating what they look like how steep they need to be. But the important thing is that along this vertical line that I just sketched in, they have to have the same slope. So whatever I'm choosing to represent a slope of positive 2, it needs to be the same for all of the dots in this line, because slopes are the same along the same x coordinate in this example. And then at 1, same deal, they're going to be like 45-degree lines, because here the slope of each, the slope is equal to 1. On the y-axis, the x-coordinate is 0, so the slope is going to be horizontal. When I get to -1, the slope is going to be -1 at each of these points. And then at -2, it's going to be, slope is going to be -2 like this. And so that's what the slope field would look like. So go ahead and on your paper, I'll draw some graphs for you to try to sketch this on, and then you can try it for yourself for the other examples. Okay, so here's what you need to put on your paper in order to try these out. Go ahead and copy this and give it a whirl, and then the answers will pop up in a sec. Okay, so here's what they look like. Over here, y prime equals y, very similar to the one I did. It's just that the slope is equal to the y coordinate instead of the x coordinate. The third one is a little bit trickier. Y prime equals x plus y. You have to add together the x and the y coordinate to see what the slope is at each point. If you notice a pattern, you actually get the same slope along diagonal lines. So like this. All those are the same slope. If we look at the second one, the second example is actually going to be one we see pretty commonly. This is actually the slope field for like a exponential function. If we know that it goes through this point, it's going to zoom up like that. If we know a particular solution goes through this point, you're going to get exponential decay. And this differential equation, y equals y prime, meaning that the function and its first derivative are the same thing, is a pretty typical pattern for exponential functions. But we'll get to that later. Okay, so sketching slope fields by hand is kind of tedious. here are some tips up here. You go ahead and pause it and write these down. On the next slide, I'm going to describe how to make slope fields in your calculator, and I want you to try that as well. Okay, so I want you to use your calculator to redo the examples we did. Y prime equals x, y prime equals y, y prime equals x plus y. So go ahead and pause it, try these in your calculator, make sure that you can generate a slope field. Drawing a slope field shows up in both the calculator active and calculator inactive sections sometimes. There's also some free response where they'll give you a differential equation, ask you which slope field goes with it. So it's really convenient to be able to pop that in your calculator and just see which one matches. So go ahead and make sure you try this. Is sometimes you're going to be given problems where instead of you having to draw the slope field, you're going to be given a slope field and you have to sketch in what the particular solutions might be. So here's a slope field, and we are asked first to sketch the particular solution that goes through the point 1 comma pi over 2. So what I'm going to do is I am going to locate the point 1 comma pi over 2. It's right here. I'm going to put a point there. And that point is going to be where I start drawing my solution. So if I move to the right, I'm just going to follow the tiny tangents. And I get something that looks like that. If I start at the point I drew and move to the left, I'm following the tiny tangents. And I'm going to get something that looks like this. So when you see a line of horizontal tiny tangents, that represents a horizontal asymptote, and we're not going to cross those. So this blue line is what the particular solution to the differential equation belonging to the slope field gives us. The next part says to draw the particular solution for the graph that goes through the point -2 comma negative pi over 2. So go to -2 comma negative pi over 2. Here's that point right here. And again, I'm going to start at that point. If I start drawing to the left, I'm going to get behavior looks like this. If I start drawing to the right, I'm going to get a graph that looks like this. And there we go. So the red graph is the particular solution that goes through there. So you just put a point where they tell you, and then you follow the contour of the tiny tangent lines. And that's basically it for slope fields. Cool. Thanks for listening, and one more video to go.